Okay. That was a great segue into the work being done at SLAC. So my name is Quynh, and I'm a staff scientist at SLAC. And I work on so my research is primarily material science, but heavily utilize the free electron laser at SLAC. And I also do R&D development for the light source itself. And Nguyen gave a very nice talk on Quynh Americ today, going into the technical details and what it does. So I will focus primarily on the scientific aspect and what we need and how Quynh Americ helped us to speed up or accelerate what we do and then become more effective or faster in terms of getting to the scientific results. And hopefully this will inspire you to develop new tools that we can use there for big data analysis and get on your priority list. So first, I mentioned before, what I do is look at different kinds of materials, in this case, is semiconductors, and so that we can try to use it in the future for new devices, both classical and quantum devices, such as sensors or quantum computers. And we do that by using different kinds of tools to look into different compositions that create a material. And here, if you look at these four different things, they are the main compositions that make up a material, including orbital, charge, lattice, and spin. And each of these constituents require a completely different technique to measure them. And each one is extremely costly and produces a lot of data, and it takes a very long time to analyze or getting to the scientific publications, which we're talking on the order of months to several years, or something like that. And because of this reason, we first propose to do the experiments, but combined with a lot of quantum chemistry or quantum material calculations with accelerated computing and machine learning to try to understand this huge amount of data, and from there draw conclusions on what we learn about the materials and how do we guide the synthesis process for new materials. So first, let me explain to you why we need different kinds of light sources. It's because you have to match the wavelength size of the light. And here I'm showing from gamma ray all the way to microwave, which is quite long. And each of these is comparable to different types of objects. So let's say if I want to measure atoms, what I would need is a burst of X-ray light, which is about angstroms. Or if I want to study molecules, then I need somewhere in ultraviolet. And for those of you who are domain experts, there's of course a sliding scale on here. And if we go to the visible, or about microns, is human cells, or about the thickness of a human hair, which is about 30 to 60 microns. Or if you go all the way to microwave, it's honeybees. So for the purpose of this talk, I will focus primarily from the X-ray range to the infrared, and how we actually make these different light sources. So it depends on what you need and what you want to study. Either you can use a tabletop laser system, where I have on the right there, or I don't know why it's getting cut off, but tabletop laser systems, or if you want X-rays or extreme ultraviolet lights, you have to go to one of these facilities, either a synchrotron or an FEL, and mostly the difference is the brightness and the time resolution. So luckily at SLAC here, we have different kinds of light sources. There are high harmonic generation in the laboratory, or this exists at many universities, where people make these very bright light sources and use them to study materials. And at SLAC, we have both a synchrotron and the free electron laser. And the main difference is, as I mentioned before, is that the synchrotron has less photons and it has longer pulses, and the FEL is much brighter and have shorter pulses. And now we have an incoming one with a lot of X-ray bursts up at the LSOS, and this is where we're going into the petabytes regime, or hundreds of petabytes regime, that we need to figure out what to do about with the luxury of having too much data. So let me go a bit more into detail on what we have here at SLAC. It's we have a 3-kilometer long accelerator. It goes underneath I-280. If when you fly in from SFO, if you look down close to SLAC, there is a straight line on the map that you can see. It's the linear accelerator. And up until this point, we operate mostly the LCOS accelerator that you have there. And last year, we just commissioned the LCOS-2, which is one of a kind in the world, and it will be the most powerful and the only one that exists. And using this tool here, we can tune the X-ray wavelengths, and we can look at many different processes from planetary biology to materials and chemistry. So since I do primarily materials science, I would focus on materials here for this talk here. And so to go into a bit more about what we study in the materials, this is a very heavy scientific talk. So there we go. So if I use infrared light or visible or one of these wavelengths, I can select exactly which electron I want to take off from a material. And that tells me a lot because now I can use it to control the electron where to go and change the material properties. And using this, I can control it using an X-ray pulse or a laser pulse on a very short time scale. But how do I see what I'm doing? The way to do it is to use different kinds of techniques. And so I divided this into 3 categories. This means spectroscopy. Spectroscopy means I study electrons. Scattering means I measure atoms. And spatial imaging, meaning you just take images of what's right in front of you. And you see both electrons and atoms at the same time. So for this here, we use Quynh numerics specifically for scattering applications where we measure atoms, see how they're moving, and how the electron density move with them. So let me describe how it works at the beamline. First, we start writing with a proposal, and then from submission to, assuming you get accepted, to performing the experiment is about a year. And within that time, you have the time to prepare. And then we now do the experiment, which from step 1 to 4, that would be about 60 hours that you get granted. It could be most likely less. And then from data collection, assuming everything is well prepared and you have a very effective team, now we can get to the data analysis where we extract the scientific insights. Here we apply fits, and this is where Quynh numeric comes in. That we need to do this, and we need to do it quickly on a short time scale so we can decide what to do next. And we have to use our resources effectively because each of these 60 hours costs about several $1 million, and we don't want to waste that. So then we get enough insights for us to move on, and it typically takes a lot of people, about 15 to 20 or more that's in the room to make decisions and then keep going. So I will go into detail on each of these steps here, but from doing all of this, then you get the new scientific insights and hopefully write up publications and publish results and then repeat the cycle if this is what you want to do. So what do I mean by data collection? So it's not just collecting data by pressing buttons. It's about first tuning the 3-kilometer accelerators. And the directorate that tuned this has about several hundred people. And then it goes to the photon size, which goes into the experimental hutches, and it divides into different kinds from chemistry, biology, materials. And each of those components have to be working in the control system to allow us to acquire data during the experiments. And then we run everything from the control room. The hutch is completely closed for safety reason because it's radioactive and you cannot be in there when the X-ray is on. So from here, now we go to what we're running in the control room at the LCOS is we try to control each of these components. Most of the things are motorized and we move things around. And the detector is on a robot where we can move the detector around to catch the signal that we're interested in. So here, what happens inside the experimental setup? There are many different parameters that you can tune. One is the laser and the X-ray, so that you can watch what the electrons and the atoms are doing as a function of time, or you can rotate the samples in different geometry and map out the entire 3D space of the object, which is, if you remember the last slide in Elliot's talk, that was diffractions, so that you can capture the orientation of the sample. So that's sort of what we're doing here, but for materials, except we know what the orientation is. And or you can also tune the temperature all the way to just a few kelvins to see how the sample change from one phase to another. All right, so how do we generate this massive amount of data that I just mentioned? So if you just take a look at this detector here, it's a multi-pixel detector, about 1,000 by 500, operating at 16 gigabits per second. And if we move the detector around, we basically capture the Fourier transform of the object in momentum space. And we purposely want to do that because we want to know where the electrons are, where the atoms are, and what they're doing. And we have to see that in momentum space. So if you take a Fourier transform of that momentum space, you will see the object in the real space. And if I change the time between the laser and X-ray, then I can map out what the electrons and the atoms are doing as a function of time, which we're talking about 10 to the minus 15 seconds or 10 to the minus 18 seconds. That's how fast things move. So what do I get out of this? So we put every single pixel to use. So if I just take a trace out of just one pixel and plot it over here, then I get a time trace. And this time trace corresponds to which direction the atoms are moving within the lattice or within the material. And if I take the Fourier transform of that, then I get what we call the phonon dispersion mode, which tells us how fast these atoms are moving and where we are within the material. So here I'm just showing a few more pictures going into detail. And this is what we use numerics for. It's not in that paper, but we just recently demonstrated how we can do this much faster or 6 times faster than before. And we can extract these insights more effectively so we can guide the experiment and acquire smart data. So in this case, I'll give you an example of what we need. So let's say we have here 6, 7 different bright spots. So what we want to decide is which bright spots do we care about and which one do we want to focus for the rest of the 60 hours. So we have this information much faster and we can decide on that and just focus on one of these. And one of these means, each of these means a different orientation of the material. So now you're picking the orientation of the material by picking one of these spots. And then by doing analysis much faster, then you can just stay in that one location. So again, then taking the inverse Fourier transform of that, I know exactly where within the material that I'm studying. That's what I get out of doing this. So doing the analysis that I just described with Quynh numeric instead of NumPy, we shrink down the extraction of the data and the processing of the data by 6 times. And it helps us to look at things much faster. And potentially it will also help us with the offline analysis after the experiments and bring us to science discovery faster. So this is with the current system that we have. And what we want to do next is with this new tool here that we just commissioned very recently, where it's a 10-year project by the Department of Energy as a collaboration between 5 different DOE labs. And we built this 1 megahertz machine where things are much faster. Instead of taking weeks to do an experiment, now it will take, to take a nice measurement, now it takes us a few days. So that's how much more efficient we are. So that's on the hardware side. So now what we need to figure out is how to configure or develop the software side so that we can also be as efficient. And what we're, and So, but to give you an idea of how much data we're going to have. So right now, each of the experiments, so for this most recent experiment that we demonstrated Quynh on, we had about 85 terabytes in total with that's with LCS1. And with the LCS2, that will be 1,000 times bigger with probably less hours. So now what do we do with that much of data? And that's equivalent to someone taking 4,000 photos per day for life. Or if you put a 1 gigabyte flash drive next to each other, petabyte size costs about 292 football fields in square footage. So we really need to figure out what to do there. And this is just an overall map of all the efforts that we're trying to do, not meant for you to understand everything, but going from the accelerator side where we generate the X-ray all the way to the photon size where we use these photons for applications. We have all kinds of projects going from control systems to data compression to developing digital twins to quick analysis. And this is where I fall in, where I develop digital twins and also trying to speed up the data analysis as much as we can so that we can make up for this 1,000 times multiplication in data production. And hopefully from there, then we can get back to doing science very effectively or efficiently. So just to give you a picture of what the LCS2 look like, here is not the whole thing yet, but one of the new hutches that's been commissioned and have see thousands of X-ray bursts per second. And with all these complex instruments here, everything have to be motorized and controlled remotely. So and then using this, we can now look at many different processes in materials that we haven't studied before. And then just in addition to this, we have all the instruments that's attached to this big beamline. So we have 5, 6 different instruments, hundreds of beam times per year, and that produce many hundreds of terabytes of data. So with that, I just wanted to conclude and thank all the people who worked on this project. All of them are here in this room, and with exception for Irina and Yana. But other than that, thanks everyone for your attention.